Thank you. Hi, everybody. How we doing? I know I'm the only thing between you and lunch right now, so bear with me. I will try not to go too far over time. I'm Anjana Vakil. You can find me on Twitter at Anjana Vakil, and there will link you to my various other online presences. And yes, as Val said, I'm going to be talking about immutable data structures today for functional JavaScript. So what I'd like to do today is talk with you all about why immutability is cool, what it is, what advantages it has, and some problems that come along with it in terms of efficiency. But we're going to look at some cool data structures that we can use to make immutable data efficient. So we're just going to get a high-level overview of kind of the intuition between these behind these data structures. And then after lunch, there's going to be another great talk by Ifan that goes in a bit more depth into some of these data structures. So get excited for that. And then at the end of the talk, I just want to tell you a little bit about some practical ways you can use these data structures in JavaScript. Who works with JavaScript? Okay, it looks like half the room has some kind of dealings with JavaScript. So yeah, if you want to take advantage of these, we'll just look at some easy ways you can do that. So really quickly, a little bit about me. Yes, I have been working on a custom query language for a company called Uber Research for the past year, but next week I'm actually starting a new job at a company called Mapbox, where I'll be working on engineering, learning, and development. And as Val just mentioned, my background is not exclusively in computers or programming. I've had a very wandering path into tech, and one of the communities that brought me back into the tech world is a really fantastic programming community in New York City called the Recurse Center that I was lucky enough to attend in 2015. And this is the place where I found out that functional programming was a thing, and that immutable data was cool, and what persistent data structures are, which we're going to talk about later. And the Recurse Center is amazing because it's the kind of place where you can go for 6 weeks or 3 months and just learn about whatever is interesting to you in the world of coding. So if you're curious, if you're into functional programming, if you're looking for a great place to kind of take a sabbatical and indulge your curiosity, check out recurse.com. It's a really great place. I'm also an alumna of a fantastic initiative called Outreachy, which is a program that offers paid remote internships to women and underrepresented folks to help them get involved in open source projects at organizations like Mozilla. And so if you or anyone you know is looking for a very cool way to get involved in the open source world with a paid internship, please check out outreachy.org. I'm also a Mozilla tech speaker, so a big fan of Mozilla, and more than happy to talk about any of these things at lunch or after the conference. Just come find me in the hallway. But we're not here to talk about really cool organizations. We're here to talk about functional programming, right? Because, as I'm sure nobody will disagree with, functional programming rocks. I was expecting more of a response to that at a functional programming conference. Jeez, I guess it's the pre-lunch dip in energy. Anyway, I think I don't need to tell you all about some of the advantages of functional programming, so I'm not going to go into detail about why, what those advantages are and why functional programming is a nice way of doing things. But one of them that goes along with the functional way of doing things is immutability. And immutability also rocks. So what is cool about immutability? Well, let's imagine we only, all of our data was mutable. We're not functional programmers yet. We're dealing with regular old data structures where I can mutate them, meaning change the data in place. So in a land of mutation, what happens when I have an array? I've got my nice little array here. It's got 8 things in it. They're numbers, they're integers. They go 0, 1, 2, 3, and it's super boring. And it's a code example, and it's boring, so it gets a boring name like foo. And I'm just like already asleep, and I'm sick of these boring code examples. So let's make it more exciting. Let's make it cuter and turn it into a zoo that doesn't have integers but has animal emoji instead. So we got a monkey at slot 0, we've got a koala at 1, a lion at 2, etc. This is much more fun to work with. Okay, but this is a mutable array. Zoo here is a mutable array, so I can just change things around, willy-nilly, however I feel like it. So if I wanted to make an even more exotic zoo, maybe I want to replace my koala at index 1 there with something a little harder to find, an alien. So now I've got my same zoo array. It is really the same array. It has the same identity. It's just that the data inside of it has changed now. So instead of a koala at position 1, I've got an alien. And I'm excited about that because I really like working with extraterrestrial beings. But that's not really cool because I might interfere with what my coworker was doing, where they had some code that was working with zoo and only expected Earth beings, Earth animals, to be in the zoo and didn't handle the edge case of there being an alien. And so I just made my coworker's day really hard. She's over there saying, "What? Who did this? Why is there an alien in the zoo? Somebody changed this out from underneath me. How could this happen? This is so sad." And so when we're working with mutable data like this, we have a couple of problems. On the one hand, we have bugs that can come from someone else or past you changing the data in a way that you weren't expecting. And in order to avoid those bugs, we end up having to put in a lot of overhead, a lot of management of who's allowed to change what, when, and which changes are okay and which are not, and when it was last. It's a lot to keep in your head. It gives you headaches. So mutability has these disadvantages. And in the world of functional programming, we say no to mutation. Mutation is cool for comic books, but it is not cool for our code. Sorry, Professor X. Mutation is not okay. And so we are going to journey to a different land, a land where all data is immutable. Meaning, once it's created, it can never be changed. Now, this is great because, as we just saw in the previous talk, discipline is hard. So, if your code forces you to never change data because it is just impossible to change it, once you've created an array, it stays that way forever, then you don't need to worry about discipline. Your code is disciplined for you. So, if our data is immutable, then what happens in our zoo? All right, so let's go back to our original zoo. I have these Earth animals. They're pretty cute, but I still want a new array that's more exciting and has an alien in it. So what do? I can't change zoo because once it's created, it always stays exactly the same. So if I want an array that's just like zoo except has an alien in it, I would have to create a new copy, the same array, in which instead of a koala at index 1, I have an alien. But then I'd have to copy over every other animal, every other piece of data in that array that didn't change. So this is good for my coworker because she was working with zoo and I didn't change zoo at all. Zoo stays exactly the same, so I didn't cause her any bugs. I didn't cause future me any bugs because zoo is always the same. I created something new. And this is what we're always doing in functional programming, right? Instead of mutating the data in place, we want to do some kind of computation and then return new data that looks the way we need it to look without changing the old data. However, this code is slow, like a turtle, because I had to copy over every single item in that array, even the ones that didn't change. And I only changed 1 out of 8, so I had to copy 7 kind of unnecessary things. And it takes up a lot of space, like a whale, because I had to allocate an entire new array the same size as my original array, so I'm using up double the space now. So this is frowny face. This is sad and worrying. Because copying, as we said, it wastes time and space. It's not an efficient way to do immutability. It is immutable. It works. I don't have the bugs on the overhead, but it's slow, and that makes us cry. So there must be a better way, right? If there weren't, I wouldn't be here talking to you all. We need a hero to come and save us from this copying problem. And that hero is persistent data structures. Persistent data structures. So, thank you. Don't thank me. Thank Phil Bagwell. Anyway, Persistent data structures and immutable data structures are two terms that are kind of often used loosey-goosey interchangeably in the industry. They are not the same thing. So when we talk about immutable data, we talk about data that once created, never changed. When we talk about persistent data structures, we're talking about data structures that are special in a different way. They're kind of like masters of time and space. Because the old versions stick around. They stay put. They stay where they are, and then new versions are created efficiently. Now, there's more terminology here and jargon and things that you would want to Google or, argue about on Reddit or whatever. I will let Ivan tell you more about the different types of persistent data structures, types of persistence after lunch. So he'll go more into that terminology. But for now, suffice it to say, for the rest of the talk, we're going to be talking about persistent immutable data structures. Data structures which are both immutable, they never change, and in which old versions stick around. So, how do these things work? These superheroes, where do they get their power from? Two really beautiful, magical things. Trees and sharing. Isn't that so nice? Sharing is a superpower, true in life, true in computer science. So, how does this work? All right. Before we had a regular old immutable array. It's cool because it's immutable, but it's slow because it's just a regular array. How can we make this more efficient using trees and sharing? So the first thing that we're going to do is we're going to take our array and split it up. Split up the values into what are going to become leaf nodes of the tree that we're going to see. Now I could have just one value per leaf, like one animal in each node, but then they might be lonely and that would be sad. So instead I put them with buddies. So there's 2 animals per leaf. We've got 2 values here. We'll talk a little bit about the number you might choose for that later. And hopefully all these animals will get along and nobody will eat each other. Tiger. Don't eat that warthog. Okay. So now we've got our array split up into little leaf nodes. What we'll do then is we'll connect them, also 2 by 2, into intermediate nodes, and keep connecting them up and up until we get a single root node that connects all of the leaves into one tree. And that now is our zoo. So instead of a simple array, we've got a tree that represents the same data. It has a little bit more structure, and we have a few more nodes here. So this is taking up a tiny bit more space, but we'll see why that's useful. How do we update things? In our old immutable array, we had to allocate an entire new array and copy over all of the values, including the one thing that we wanted to update. In our tree, in our persistent data structure, what we have to do is only copy the single leaf node that has the value that we want to update. So in this case, if I want to update the value at 1 from a koala to an alien, I'm going to make a new leaf node that's kind of a copy of the 0, 1 leaf that now still has that monkey at 0, but now has an alien at 1. So I did have to do a little bit of extra copying, but much less. I didn't have to copy any of the other animals that didn't change. Then what I'll do is create new intermediate nodes that link the new copy of my leaf node to whatever the old copy was paired up with before. So I create a new intermediate node here that pairs up my 0, 1 node with my 2, 3 node, and keep going like that all the way up the tree, creating new links to the new node that I've made. Until ultimately we get a new root that connects the new node with all of the unchanged nodes, and that is going to be my new data structure. So what we've just done is we've copied everything from the leaf that I wanted to update all the way up the path to the root node. This is called path copying, unsurprisingly. And that's cool because I only had to copy the nodes on that path from the leaf to the root instead of all of the other nodes with the values that I care about. And the rest of those nodes, which are now in pink here, those are shared between the old version and the new updated version. This is taking advantage of what we call structural sharing. We're sharing most of the structure of the tree between the 2 versions, so we don't have to copy all of those other nodes. Now, in this tree, we don't have too many nodes because a lot of things don't fit on a slide, but You can imagine that as your data structures get more complex, you're going to have the vast majority of your data stay the same and be shared between new version and old version. And only the nodes on that path need to be copied. So, this is great. We're reusing most of our data. We didn't have to copy so much over. We had one little extra copy here, but that's much better than 7 extra values to copy. So these two beautiful concepts, trees and sharing, turn immutable data structures like plain old arrays, which were slow and took up a lot of space, into much more performant immutable data structures, which move much faster. We have a much quicker time complexity and take up less space because we are able to reuse some of those nodes, some of those values, instead of copying them all over. So we go from the turtle to a racehorse, and we go from a big old whale to a little shrimpy guy. Okay, so what about when we want to look up something in our data structure? How do we access things? And this is where it turns out that the tree that we've been using has had a secret identity all along. Dun, dun, dun. It has really been a tree. What? No. Our TREE tree has actually been a TRIE tree. TRIE from the word retrieval, because this is a data structure that's often used for retrieval, although usually it's pronounced try to distinguish it from TREE tree, so I'll say try, or at least I'll try to remember to say try. Okay, so a try is a special type of tree where the leaves hold values. As we saw, the animals are all in the little leaf nodes, and the path from the value to the root represents the key with which that value is associated. So often these are used for doing things like storing dictionaries. Let's say I had a dictionary where I'm mapping names of animals to the actual animal emoji, which is the most important part. In this type of data structure, what I do is from the root, I would have a branch for each of the first letters that I might encounter for an animal name. And if I want to look up an animal like ape by its name, I would start with the A branch, and then from there I would go to the next letter. I would have different branches for all of the possible next letters, so I would take the P branch, and then from there I would have an E branch, and ultimately I would end up at my ape. This is also sometimes called a prefix tree, which makes sense because at each level of the tree we have a prefix of the word, of the key that we're associating with each value. So how does this work for arrays? We're talking about arrays where we have an index, not a word. The insight here is that if we take our index, our integer, and convert it to binary, then we have something like a binary word where we can go letter by letter, bit by bit, through the word down the tree. So that's how lookup works with these array type structures. Let's see how that looks. This is the same data structure as before. I've just annotated the branches. We always had a left and a right branch. I'm just calling them 0 and 1 now. When I want to look up a particular index, let's say I want to see what's at index 5 of my array. I take that index and convert it to binary. So 5 is 101. Then I go bit by bit from the root of the tree to the 1 side, then the 0 side, then the 1 side. So I take the right branch, then the left branch, and then the right node, and I end up at the value associated with index 5, so 101. Works basically just like letter by letter, only we're using bits. Cool. Hopefully. So what is this thing? Is it a bird? Is it a plane? Is it Superman? No, it's a bitmap vector trie. Yeah, I don't know. It's not a very catchy name. Thank you. You'd also sometimes hear these referred to as bit partitioned vector tries. So if you want to Google something because you're just sitting there super bored and you just want to look on Google instead, go Google that. Just kidding. Don't Google during my talk. So we are all into things like big O notation, so let's talk time complexity. Woo! Yeah. All right, the immutable arrays that we saw before, plain old arrays. They have really fast lookup, right? They're arrays. Constant time lookup, O1. However, as we saw, when I want to update something, I have to copy the entire array. So that's linear time. That's pretty slow. Whereas with our trees, with our bitmap vector tries, these cool persistent data structures, we have to look through the entire path from the root to the leaf anytime we want to either update something or look up something. So that's going to be logarithmic complexity, logarithmic in the length of our array type structure, or our vector here, for both lookups and updates. So we've got we've got faster updates, but we've also lost some time on the lookups, right? Because logarithmic complexity is not amazing when you're dealing with like these long numbers. You're still going to have to go through a lot of digits. Like if I have an index like 18,977 and I convert that to binary, which I'm sure you all know the binary for 18,977 in your head, right? It's this. 15 digits of ones and zeros. I don't know. Whatever. Anyway, if I have to go from the root down 1 and 0 and 0 and 1 and 0 and 1 and 0 and 0, that's still going to take forever. Still not very fast. The good news is, what we're doing here is we're going one bit at a time, because we only have 2 branches at each level of our tree. Each node only has 2 options. But nobody said we need to do that. Nobody said that the tree has to be only 2 branches at a time. If we do it that way, we're basically representing 1 bit of information at each level, at each node of the tree. We have a 1 or a 0. And nobody said that we can't represent more information at each level and have more branches correspondingly. So we can choose the number of branches of our nodes. If we have fewer branches, like 2, we're going to end up with those deep trees, as we saw. But the advantage is we have small nodes. As we saw in the example, when I want to update a node, I only had to copy 1 extra thing. So that's good because we save space and time. But if we have more branches, then we trade everything off. We can have shallower trees, but at the same time, our nodes are going to have to be larger to accommodate the values or the pointers to each of those different branches. So folks have done some studies on this, research about, in practice, what ends up being a good trade-off. And it will depend on your application and whatnot, but generally, the best balance seems to be 32-way branching. So 32 slots in each node, aka representing 5 bits of information at each level of the tree. So what that then looks like, if we have this big old 15-digit binary number representing our index here, is instead of having to go through 15 levels, I only have to go through 3. Because if I have 32 slots in each node, in each level of the tree, I can consume 5 bits of information at a time. So we've got a shallower tree. I see how excited you all are by this. I feel the excitement. Okay, so the point is, it's a trade-off. You can choose. But if we do use 32 for our branching factor here, there's some good news. We said that our bitmap vector tries, these trees have basically logarithmic lookup and update complexity. But if the base of that logarithm is 32, we're going to get some pretty small numbers. Like, okay, pop quiz. Does anybody know what the largest number you could possibly represent in JavaScript is? No. It's big, huh?
2 billions? 2.7 billion.
Good guess. That's what I thought. And I actually, in a previous version of this talk, I said, and it turns out that that is true for like if you're doing bitwise operators. But you can actually go even further to like, I don't know, 9 quadrillion and something or other. There's like 15 digits in that. It's a really big number. I don't think you're ever going to have 9 quadrillion elements in your array. Maybe you will. Maybe you're an overachiever. But even if you had 9 quadrillion elements in your array, anybody happen to know off the top of their head log base 32 of 9 quadrillion? No, I didn't either. I looked it up. It's like 10.6. So that's a pretty small number. So what ends up happening here is that, yes, technically it's logarithmic complexity in the size of the array, but this base is so big that we're going to end up with such small numbers that we often hear this talked about as effectively constant time. Because for any practical purpose, you're going to have such small numbers that you can wave your hands and say, yeah, whatever, it's basically constant time. So that's cool, because we haven't lost much time on lookups, And we've saved a lot of time on updates. Okay. So far I've been talking about array type things where we have indices. We have integers associated with each value. But what about more object type things or map type things where we have arbitrary keys, let's say strings or, well, really anything, because in an immutable world, we could use almost anything as a key. Let's say strings, though. How do we represent something like a dictionary or a map or something like a JavaScript object? So, for example, maybe I want to have my tree, instead of having numbers and indices for each animal, maybe I want to have like the first letter of their name, like M for monkey and K for koala and G for gorilla, etc. How would I represent this? Well, it's a really simple insight, but basically, you can just hash the key, and then you get a number, some kind of arbitrary number. Once you have a number, you can do it the same way. You can convert it to binary and descend the tree just like before. The objects won't be in the same order, but who cares? It's an object. We don't usually keep the keys in order, right? We don't need that. So the way this works is I want to look up something at the key. I want to see what value G has, the string G has in my data structure. I take some hash function, which gives me a number for G. In this case, we're going to make it a nice convenient number, like 5, because slide examples are hard. And then I convert that to binary, just like before, and everything works pretty much the same. I have a binary number, I break that down into letters. We've gone back to two-way branching, because again, slides. It's hard to put 32 branches on a slide. But basically, the logic is the same. The basic intuition is the same here. So this is really cool, because anything I can hash now, I can use as a key. So I can use whatever I want. And if all of my data is immutable, I can hash anything, because it's never going to change. So yay, I can use whatever. So this is great. We've covered pretty much, major use cases of how we would want to take advantage of these data structures. And this more object type thing, if you want to Google it, you can Google hash array mapped try. Abbreviated HAMT, or HAMT, which I think is a really funny nickname for a data structure. Hey, HAMT, how you doing? I don't know. Anyway, this is a cool type of data structure pioneered by a guy named Phil Bagwell, who wrote a couple of, or several surprisingly accessible academic papers on these data structures. And then folks like Rich Hickey, who created Clojure, took this idea, ran with it, and implemented these in Clojure, for example, and also extended it to things like the bitmap vector try. And other languages like Scala sort of implemented them around, or kind of in parallel. And there's implementations of these in lots of languages, even non-functional languages. Pretty much, if you don't work in Clojure or Scala or JavaScript, which I'll tell you how to use these in just a moment, you can just Google it. You can find implementations of libraries to let you use persistent data structures in pretty much any language you might want to work in. Okay, but just to recap, mutability makes our heads hurt because we have the possibility of changing things out from under ourselves or out from under our coworkers, and we have to manage all of that, and it's hard and it hurts our brains. So instead, we go for immutability, which rocks, because once I've got some data, I know it's never going to change. However, if I do naive approach to immutability, where I'm just copying things over all the time, that leads to really slow and really space-consuming programs. Whereas if I use these awesome persistent data structures with trees and structural sharing, I get immutable data that is much more performant, both in terms of time and takes up much less space, because I'm sharing values between versions. Alrighty, so still have a little bit of time left. So we can now see, all right, hopefully I've convinced you by this point that these data structures are like pretty cool. And we might want to use them in a handy-dandy language like JavaScript, let's say. So how could we do that? Well, good news. We don't have to go read Phil Bagwell papers and implement these from scratch with all of the clever optimizations that folks like Rich Hickey and all of the Clojurians and and Scalaians. What's the word for a person who uses Scala or Scalarian? Scala? Anyway, we don't have to go through and reinvent the wheel and do all those clever optimizations, which Ivan is going to tell you a bit about after lunch. We can just use libraries. Yay! So there's a variety of options in any language, like I said, but in JavaScript, just for example, there's a variety of different libraries that we could use. I'm just going to show you a couple, but basically you can look this up and you can find a lot of alternatives. So if you don't like either of these, there are other options. The first one I want to tell you about is Immutable.js. Maybe some of you have worked with it. It was created by Lee Byron at Facebook. And so being part of the kind of Facebook ecosystem, it fits nicely with the React world and is often used kind of in conjunction. And basically this offers pure JavaScript implementations of these types of data structures. So what's nice about this library is that when you use it, you really feel, it feels like JavaScript. It feels like regular old mutable JavaScript data structures. Just to look really quickly at how it feels to use, when I want to create something like a persistent vector or array, the name for the data structure I'd probably use is a list, and create it with this cool kind of weird naming of immutable.list.of, and then pass in as arguments the values that I want my list to have. So I'm creating here a list A, which is immutable.list of 1 and 2. That gives me a list object, which is, it looks like a JavaScript array, but it's not. It's a special type of object called a list. It's different. And it has methods that we might expect, like, for example, push. I can do a.push3. However, although it seems like this would be updating A in place, like a regular array, it is not. It's creating a new copy, a new version of A that I can capture as A2. And I can prove to myself that A hasn't changed using checking the size. A.size is still 2, whereas A2.size is going to be 3. And if I want to see what's at index 2 of A2, I can use the get method. So I can do A2.get2, and I get the 3 out. So I can prove to myself that A didn't really change. And similarly, for object type, key value pair data structures, we have maps in Immutable.js, and the creation is similar, although we don't use of. I don't know. We pass in a JavaScript object, basically associating the keys that we want with the values that we want them to have. So I'm creating immutable map of where A is associated with 1 and B is associated with 2, and then I can use things like the set method to update that map. But again, it looks like it's going to be changing it in place, but it's not. It's creating a new copy and returning that. So I can capture that as O2 here, and using the get method, I can prove to myself that the value of A in O was never changed. A stayed to be, remains 1. Whereas in O2, I set A to 3, and so O2 is really a different copy, different object. So that's how it works in Immutable.js. Now, I don't know how you all feel as functional programmers, but I feel like if I'm trying to get into the functional mindset and have that, discipline, as we just heard, I don't really want to try switching back to this kind of object-oriented dot methods and things like that. Personally, I'd like to do things in a bit more functional style, where we're using pure functions and passing in the objects that we want to do something with as arguments. So for that, one library that I like to use is called Mori. It was created by David Nolan, and it's basically a ClojureScript port. So bringing ClojureScript into the beauty of ClojureScript's persistent data structures into vanilla JavaScript. So the way this works feels a lot less like JavaScript and a lot more like Clojure. In terms of the functions and their names and that sort of thing. But personally, I like it because it lets me stay in that more functional mindset. So just to look at basically these same really simple examples with Mori. In Mori, the list type data structure that I'd probably want to use is, well, there's also lists, but for most things, I'd probably use a vector. And I can create it with, just this function, mori.vector, which returns a thing that doesn't look so much like JavaScript anymore. You'll see we're missing some of the commas and the syntax looks more like Clojure. I have functions like conj, which allowed me to sort of append something to my list here. So I'm gonna, now we see that the difference here. This is more like a function, this conj function, which takes in the original array, A, as an argument, and then the value to be appended, and returns a new vector, which I can call A2. And as before, I can use these, I can use a bunch of kind of helper functions in Mori, like count and get, to show myself that A never changes. When I conj something onto A, it creates a new copy called A2. And in Mori, the more object type or map thing is, it's just called a hash map. Again, it's a little bit, this looks a little bit less like JavaScript, a little bit more like Clojure. So I can create a hash map by calling this hash map function on just a series of arguments where I alternate key value, key value. And this gives me something which, again, is missing our familiar JavaScript colons and JavaScript commas and all of that stuff. It looks a bit more like Clojure. There are other functions I can use, like instead of setting things, I have this assoc function to associate a new value with a given key. And that, again, gives us a new version. It's an entirely new object. And I can use the get function to get the value of a particular key in both my old data structure and the new one and prove to myself that the old one didn't change. So these are really, really simple examples, but just to give you a sense of the feel, this is kind of the main, to me, the main differentiating factor between these two types of approaches you could take. You could go the more JavaScript feel, object-oriented approach of Immutable.js, or you could go the more pure functions, passing around data structures as arguments to those functions, which is the approach taken by Mori. Now, there are a few other differences. As I said, Mori is from the ClojureScript world. Immutable.js is just JavaScript through and through. You might have feelings about that. I don't know. Immutable.js is a bit smaller, so if you want to be loading this on the client side, it might make sense. Mori, it works really good with Node, for example. Mori, though, doesn't seem to have been updated in the past couple of years, so I'm not entirely sure what the future of that will hold. But in any case, it's a good way also, if you're curious about Clojure, but you do JavaScript and you want to sort of get a feel for some of the Clojure-iness, it's a good bridge. And if you don't like either of these, there's plenty of other options. For example, I'd suggest you check out one called Seamless Immutable by Richard Feldman, who is an Elmer. This one has a nice advantage of you can choose between the object-oriented API and the functional API. It kind of allows you to pick your poison or your persistence. So those are the libraries I wanted to talk about. This is basically just a little taster of some things you can use in JavaScript. And as I said, if you're not a JavaScript programmer, for the other half of the people, you can find whatever the libraries, the implementations of persistent data structures are out there for your language. Like for Python, for example, there's a very cleverly named PySystems library. Anyway, what I'd like you to take away from this is just that immutability rocks. Functional programming and immutability go hand in hand, but if we want to do it efficiently, we need these more clever data structures. We can't just do the naive approach to making copies of everything all the time. So I hope from this you will take away a couple of useful things to Google and things to look up on GitHub, and you will go forth and live long and not mutate your data. So thanks very much. Благодаря.